All right. It is 7:05. You can go start. You can go ahead and start. Uh, Quick introduction. My name is Frank. I'm being joined by Justin and Safa. So let me move on to the next slide. All right. So welcome to the exam review. If you guys have any questions at all throughout this whole, oh, okay. I figure something. All right. So the first topic we're gonna cover. So this test's going to be going over chapter 14, 15, 16, and 17. For 14, it's going to be about like ethers, epoxides, thioesters, how to make them, and how they react. So for ethers, the general formula for that is going to be you have two R groups in the middle of an oxygen. Remember, the oxygen is going to be sp3 hybridized. The individual bonds, CO bonds, are polar. Uh, Ethers, they cannot hydrogen bond with each other, but they can do so with waters and alcohols. And so you're going to see a lot of ethers in solvents, and a special ether would be like a what we call an epoxide, which is a ring. There's other ones like it, like tetrahydrofuran, but um, usually this chapter is going to be focused on like ethers and epoxides specifically. On the other hand, you have thioethers, which is kind of the same thing as ethers, but instead of an oxygen, it's a sulfur. You see this in ozonolysis, also like DMS. That's dimethyl sulfur. So it's used as a reducing agent. All right. So how do you make an ether? So you can make ethers by reacting out, like, using really some ether synthesis, where you start off with an alcohol. Um, yeah, you start with an alcohol. You would deprotonate it using a um, like NaK, NaH, or any strong base. And so with that, you can react it with a primary leaving group. So essentially a SN2 reaction, and that should give you a an ether. So in this example, our leaving group would be the tosylate. Right. And so if you're reacting two alcohols together, one of the alcohols would be the alkoxide, so you would deprotonate one of them, and the other one you would just tosylate it. So you're in order to combine two alcohols together. Right? This works pretty much the same way for thioethers, where um, one of the thiols are deprotonated, so you would get like a thiolate with a negative charge, and then you would just react it with another primary leaving group to make a sulfur ether. All right, and so another way you can make an ether is through condensation. What you do is just you have two alcohols together, you react it with sulfuric acid and heat. So here, um, essentially, water is going to come out of it, and you would combine these two R groups together with oxygen in the middle. Another way to make an ether is if you have an alkene. So if you have an alkene, what you can do is do an alkoxymercuration, demercuration. So this would be the reagents. You have this mercury with um, this acetate portion of it along with a base. So by the first step, this would get rid of this double bond and attach. One of them will attach to mercury and the other one will attach to ether. The second step would be adding NaBH4. Here, this would remove this mercury and replace it with a hydrogen. Another another reaction you can do is reacting it with MCPBA or any peroxy acid. So peroxy acid is anything that has like this format where you have this carbonyl and two adjacent oxygen in a chain. So it's going to make this epoxide with a three-membered ring with a oxygen at the tip, and it's going to attach to the most substituted alkene. So if we have this molecule, it's going to attach the one that has the more substituents. All right. Next slide. Okay. Um, Another way you can do that is it's gonna be over chapter 14. 14 is just synthesis. Well, it's just reactions with epoxides and ethers, which should be on the exam. So I just put 14 in there. But here, well, it's kind of similar, where instead of on the other one, not this one, it's kind of similar to this one, but instead of mercury, you're using to um, halogen in water to get rid of the double bond. You'd also need to react it with a base. So to get rid of this, to make this alcohol into a nucleophile that will attack itself. So it's more of a internal SN2 attack if you use this mechanism. Alright, so for reactions, so one of the important reactions is ether cleavage. So it's when you react, it's usually like HBr or HI and heat. So it's a SN2 reaction where the ether gets a hydrogen from HBr or HI, and it'll make this positive oxygen with a H right here. And once you make this, you just do a regular SN2 attack with the other portion of the reagent. And because this is positively charged, it wants to become neutral. So it's going to be a good leaving group for this reaction. So this I is going to attach the adjacent carbon, and this portion of the ether will leave. And so you'll end up with two molecules. And then if we have excess of reagents, it's going to do it again. So it's going to do the same process where it gets protonated and then another SN2 attack. So for this molecule in particular, you're going to end up with um, two moles of this ethyl iodide. Okay. So let's say you have an epoxide and you want to add an R group. So you do that by uh, opening up the epoxide. So when you open up the epoxide, you're going to end up with a alcohol and the nucleophile that you're attaching. So in acidic conditions, this oxygen will grab an H. And so by doing so, this makes it a good leaving group. However, um, this is kind of special. It kind of does like SN1. So it will actually, this portion of the epoxide will actually leave. So you will form a stable carbocation, And so using acid, you are able to attack the nucleophile at the most substituted carbon, or at least the most stable carbocation. On the other hand, you have the basic, in basic conditions. It doesn't have to be like an OH, it just has to be a strong nucleophile. If you just have a strong nucleophile, you can just attach it to the least substituted part of the epoxide, which in this case, it's the number 2 carbon. And here, notice how the stereochemistry changed from a wedge to a dash. So the main difference here is with acid, the nucleophile usually is going to be a weak nucleophile, maybe like an alcohol or with an R group. With this one, basic, usually you can accomplish this using a strong nucleophile. So with acid, it's SN1. It's kind of like SN1, and then basic, it's SN2. Both will do a backside attack. So remember to draw a inversion of stereochemistry. And here's the summary of it. If you have acid, if it's acidic, it's going to attach to the most substituted. If it's basic, then it's going to attach to the least substituted. Okay. You can also react epoxides with Grignards or organolithiums. So it's still going to be an SN2 attack um, because these are strong nucleophiles. So strong nucleophiles always attacks the less hindered carbon. So it's going to attack this carbon right here. And it works for Grignard or organolithiums. And these are just the ether is the solvent and the acid is there for workup. Oh wait, the acid here is to open up the ring actually. To help open up the ring. Alright, so chapter 15 is a big part of this is conjugate systems, Diels-Alder, and molecular orbitals. So conjugated systems, they're just double bonds separated by one single bond. So when you have that, like this sequence, this is going to be a conjugated double bond. And when it's conjugated, it takes less energy to form. So here, this would be you would stable kind of double bond. You have any other questions? You guys have any questions? All right. So with molecular orbitals, you usually see this in conjugated systems, kind of like a diene. So for this specific molecule, this butadiene, um, so you're gonna each of these atoms or carbons are going to be sp2, and each carbon will have p orbitals on it because it's sp2, and so they're going to be like positive or negative. When they match, you can create like a pi bond. When they don't match, that's what we call a node or anti-bonding. So there's not going to be a bond if it's opposite orientation. Okay. So a good way to think about how many molecular orbitals you can draw is the number of lobes you have correlates to how many drawings of molecular orbitals you have. You have the highest energy at the top, lowest energy at the bottom, and these arrows right here, these correspond to the number of pi electrons that your molecule has. So for butadiene, right, you have two double bonds. When you have two double bonds, you have four pi electrons, which we fill up from bottom to top, right? And so so you would have, once you draw this molecular orbital, you would cut it in half. So where it stops, where the occupied orbitals stop, hold on, here it is. Okay, wherever the filled orbitals stop, that's where the anti-bonding line is. And then HOMO means highest occupied molecular orbital, and LUMO means lowest unoccupied molecular orbital. So for HOMO, um, since these two are our only occupied molecular orbitals, the highest one would be the one on top because it's higher in energy. And then for unoccupied, since these are our only two unoccupied orbitals, the lower one will be our LUMO, which means lowest unoccupied, so lowest in energy. All right, so when you do have a diene, there's going to be like 1, 2, 1, 4 addition. You'll also hear this as kinetic or thermodynamic control. With a kinetic, you would do a 1-2 product where it will attach, well, both um, of the reagent that you're attaching, so H and Br, will attach to the 1-2. And then the hot or thermodynamic control, you will attach it to the 1-4. So the first one and the last one with a double bond in the middle. So with kinetic control, it's cold. It's for cold temperatures. So the first thing you need to do is form the most stable carbocation. Um, so one of the double bonds will grab an H from the reagent, or a Cl if you just have Cl2. You can do like Br2 as well. Just you'll attach one of the atoms. Typically, it's going to grab the H first because you want to make a stable carbocation. Once you make a stable carbocation, then you can attach the nucleophile or the rest of the reagent. Right. So here, it grabs the H, makes a. Here, this would be a secondary carbocation, um, which is better than a primary carbocation. So this would be our intermediate. Um, but the next step was to attach a nucleophile. So once we form the carbocation, we just attach it to the carbocation, and we should be able to get this 1-2 addition. For the difference between this and the thermodynamic one is you resonate it after you form the carbocation. So here you form the stable carbocation. The extra step you have to do is resonate it. Whichever carbon your cation lands on, which in this case it's this one, um, that's where you attach the bromine or the nucleophile of the reagent. So this would be your product. Okay. All right. So now let's talk about the Diels-Alder reaction. It's it's when you have a diene and a dienophile, and you make like a ring with an alkene. It's also called a 4+2 cycloaddition because you have 4 pi electrons here and 2 pi electrons here. And an important thing you need to know is this diene has to be cis, in a cis orientation like this, in order to react. Right? So when you're ranking the diene on how fast it reacts, uh, we want to consider steric hindrance, and we want the diene to be open and cis. So looking at this, this is stuck at trans because I can't rotate this to where it'll look um, like this. So whenever you have a trans, this will not do Diels-Alder. On the other hand, if it's stuck on that orientation, then that's going to be the fastest one. However, if you can't, if it's not stuck on cis or trans, you then look at your substituents. If your substituents are cis like this, it creates like a steric hindrance here, and so this will be less stable compared to this molecule over here, where the the ends of the alkenes are open. So how do they react? So another way you can look at is the molecular diagram of the two molecules. So remember that the lobes have to match to form a bond. So our diene will always be the HOMO. Dienophile is going to be the LUMO. The reason why is we want dienophile is what needs electrons, so it will receive the electrons, and then dienophile is what's doing the receiving, and then whichever is the one doing the donating, the electrons will be the HOMO. So the reason why these two react, or the reason why these two connect to each other, is because these orbitals match up with the orbitals over here, the ends of this molecular orbital. All right, so another rule that we need to know is what endo is, or like with the endo rule. Electron withdrawing groups are endo, so it's if I were to draw like a like bicyclic ring right like this, it's going to be pointing downwards. That's because it wants to be close to this double bond as much as possible, because they're electron withdrawing groups, right? They want to be near where all the electrons are. That's why they're pointing downwards. Right. So here's a kind of neat trick. If your endo is a dash, then your trans will also be dash for the diene at least, and then your cis will be a wedge. However, if you want to make your endo a wedge, then you would have to flip the substituent stereochemistries. Right. The second rule is you never form the 1,3 product. 1,3 product means when you count from you're counting from the substituents of each molecule. So here, um, in this case, would be 1, this would be 2, and this would be 3. So when you have a 1,3 product, if you ever read an answer and you see that it's 1,3, you can that's an easy way to know that it's not the correct answer. So it's always going to be 1, 2, or 1, 4. Yeah. So another way to think about it is if you have a donating group here, it wants to donate electrons. So push it's gonna push this um, double bond away from it because I'm adding electrons, and if I push this double bond away, I'm gonna get a positive charge here. And then if I have a withdrawing group, I'm pulling electrons towards me, right? So I'm gonna attract this double bond towards the withdrawing group. So this carbon will be slightly negative. And so with Diels-Alder, it's kind of like a opposites attract kind of deal. So here, positive and negative, positive and negative. That's how you make the bond. Similarly with the 1,4, if I have a donating group here, I'm gonna push the electrons away because I'm adding more, I'm donating the electrons. So to make room for those electrons, this um, double bond will have to move over here. Great. Okay. Right. Here's another. Here's another example. So if you do that same thing, if they are the opposite, all you need to do is flip them, and then once you flip them, then you can just draw a bond between those two carbons. Another thing that might be an exam is the forbidden cycle addition. So that's when you have a 2+2 or 4+4 addition. The reason why it's forbidden is because the lobes do not match. So here, this side matches. So if you have a 2+2, so um, two carbon double bond right here. The other orbital does not match, so it's just gonna be anti-bonding. So what you need to do is react it with light, and that will flip the HOMO to where it'll match the LUMO. And so with this, by adding light, I can bond both sides and oops, and get like in this case, it'll be like a square. With 4+4, it's gonna make a 8-member ring. So it's kind of similar concept where by adding light, I flip one of the orbitals, and that way the HOMO and LUMO will be able to connect. Okay. So with UV spectroscopy, it's about like wavelength. So if you have conjugation, you're gonna see a longer wavelength. More substituents also means longer wavelength. So here's an example: this regular diene versus this with substituents. By adding substituents, I increase the wavelength. Um, yeah. So also, if I compare this diene with this triene, by adding more conjugation, I'm also increasing the wavelength as well. All right, so chapter 16 is going to be about benzenes, the molecular orbitals of benzenes, or rings in particular, and aromaticity. All right, so benzene is also known as 6-annuline. All carbons are sp2 hybridized. It has IR of 1600. Usually, if there's a benzene fragment, it's gonna weigh about like 77. The HNMR for benzene is 7 to 8. Yeah, so if you have two substituents next to each other, this is what we call ortho. If it has one carbon in the middle that's separating it, that's what we call meta. And then if it's directly opposite of it, that's what we call para. Right, so looking at the orbital for benzene, uh, so the number of nodes increase from bottom to top. So this is the same thing as the regular orbitals for a diene, where the highest energy is at the top, lowest energy is at the bottom. I think, yeah, so polygon rule also plays a part in this. So what that means is the energy diagram has the same shape as the molecule. So with the vertex always at the bottom. So looking at benzene, well, we make sure the vertex is at the bottom, and then we draw the rest of the shape. And each vertex, you could say that it's a individual molecular orbital. So since we have 6 pi electrons on benzene ring, I would start from the bottom with the arrows. So 1, 2, and then 3, 4, 5, and 6. So that since the bottom 3 are filled up, that means our anti-bonding line would be separating 1, 2, and 3 with 4, 5, and 6. Yeah. So same with the other polygons or other rings. With cyclobutadiene, um, it has 4 pi electrons, so you jot 2 here. So this is kind of like a Gen Chem thing. So if you have so electrons will always occupy the unoccupied orbitals first. So at the same level at least. So here, since this orbital is by itself, it would fill it up all the way. Yeah, Hunchrow. Thanks, Caleb. And then since we have 2 left and 2 orbitals left, then you would put 1 at each unoccupied orbital. So if you have one electron or no electrons, that's where you can draw the non-bonding line. So um, this isn't occupied, so it would still be considered non-bonding. Yeah. All right. So aromaticity. To For aromaticity, there's some requirements that you have to consider first. First, the molecule has to be cyclic. The molecule has to be have all conjugated double bonds. All the atoms have to be sp2 hybridized, and it has to be flat. I highlighted this because some people might look at this and say, oh, it's 4 electrons. It's probably anti-aromatic, but it's actually non-aromatic because you have 2 sp3 carbons right here. So that's what you call planar. Typically, with planar molecules, all molecules are going to be somewhat planar. However, the larger your molecule is, the less planar it gets. So an example would be an 8-membered ring. I think that's where it stops being planar. So if you have, see if I can draw it. Uh, yeah, greater than 8. Interesting. So kind of like this. Uh, so an 8-membered ring like this. If I were to make this, it's not going to be completely flat because of like sterics. Yeah, this only applies to like single rings. But in this case, because it's not planar, this is actually non-aromatic. Um, yes, it is 8 pi electrons for Huckel's rule, but because it's not planar, it would be non-aromatic. Here's Huckel's rule. So for aromatic, it needs to have 4n plus 2 pi electrons, so either 6, 10, and so on. For anti-aromatic, it's just 4n, so that's 4, 8, and 12 pi electrons. So you would apply this rule once all the criteria has been met. And yeah, so here's the example that I was talking about. So 8 pi electrons. Um, this is what it would look like if I were to make it. It won't be, it cannot be flat. So because of this not flatness, it's going to be non-aromatic. Okay. All right. So what if you have anions and cations on the ring? So if you have a cation, count it as 0 pi electrons. If you have anion, count it as like 2 pi electrons. If you were to react a ring that will make it less stable, the reaction will likely not occur. So if I react a ring and it goes from aromatic to non-aromatic, it'll be unfavorable. But it would be favorable from going the other way. So if it going from anti-aromatic to aromatic, then that would make it more stable. So the reaction would likely happen. Another thing to remember that atoms with lone pairs that neighbor sp2 atoms are also sp2. So if an atom has lone pairs and it's next to an sp2 atom, then that atom is also sp2. So let's look at cyclopentadiene. Let's say I dehydrate this, right? So I basically remove this OH. I went from a non-aromatic ring to a anti-aromatic ring, right? Because I have 4 pi electrons here. And so this will not occur because I went from non-aromatic to anti-aromatic. However, if I deprotonate this ring, I would get a anion here. So if I count all the pi electrons, I would get 6. So that would be aromatic. So this reaction will happen because I'm going to a more stable product. Another win for heptatriene. Um, for this one, it would be anti-aromatic because you would have 8 pi electrons. You have 2, 4, 6, 8, but would be aromatic if it's a cation because you would have 6 here. Right. Remember that all the carbons have to be sp2. So although this one has an anion, it wouldn't. You would. This one would have 6 pi electrons, but because this is sp3, it would still be non-aromatic. Yeah, all carbons have to be sp2 for you to start applying Huckel's rule. Right, and then so with that, let's talk about basicity. So a cyclic molecule is more basic if obtaining an H does not make it unstable. So let's look at this molecule. If I obtain an H, so if these if these lone pairs obtain an H, I went from aromatic because I have 6 pi electrons here to still having 6, so it's still aromatic. So this reaction would still happen. However, if I have something like this, where I have 6 pi electrons over here, and I use 2 lone pairs to grab a hydrogen, it went from being sp2 to sp3. So it went from aromatic to non-aromatic, and so this reaction will not be favorable, meaning it is not basic. It's basic when it can grab a hydrogen. Right, so here's more examples. So the blue ones are pi electrons, and the yellow are sigma or sp2 electrons. So this one would be basic. These these two pairs would be basic because they're not contributing to the aromaticity. However, this lone pair is contributing to the aromaticity, so this will not be basic, but this is basic. All right, so moving on to chapter 17, which should be the last chapter for this exam. We're going to talk about sigma complex, the electrophilic aromatic substitution, nucleophilic aromatic substitution, and other aromatic reactions. So electrophilic aromatic substitution. Well, first we got to talk about the sigma complex. So sigma complex is when it's the resonance structure of the rhenium ion. So when it grabs a electrophile, it's going to leave behind a cation, and that cation is going to resonate throughout the ring, and this resonance is what we call the sigma complex. So it's where the cation lands on as it resonates, right? And then usually these types of reactions will finish off with a base that will do elimination and close off that and make this ring back to a benzene ring. Okay. Right, so first reaction will be bromination, which is just adding Br2 and FeBr3. This FeBr3 is this catalyst that will make Br2 into a electrophile actually. So it's gonna make this bromine into having a positive charge, and where this double bond can grab onto the bromine. And it's similar to chlorination as well. You can use AlCl3 or FeCl3. It works the same way. So you just add the chlorine. With chlorination though, if I add Cl2 and a lot of heat and pressure, or even light, I can completely saturate it with chlorine. So this is very, I guess, dangerous. So usually we just want to add one chlorine, but just know that if I add a lot of heat and pressure with chlorine gas, it's gonna turn this into a ring with all chlorines. Alright, so the other one is iodination. So if you want to add a iodine, it's just half moles of I2 and 1 mole of HNO3, and that should give me a um, a iodide. If I want to add a nitro group, I just use HNO3 and H2SO4, then it'll add on. If I want to add an amino group, which is NH2, I would add a nitro group first. So I would do this reaction first, the HNO3 H2SO4, right? And then I would reduce it using zinc and hydrochloric acid, and that should give me NH2. If I want to add a sulfonic acid, which is SO3H, like this, I would just do SO3 and sulfuric acid. It's special about this. It is reversible, so I can add sulfuric acid again with heat, and I could remove it. All right, so what if your benzene ring has substituents, right? So typically, when you have a donating group, electron donating group, it's gonna act like an activator. So it's gonna activate the benzene ring, whereas withdrawing groups will deactivate it. So activated benzene rings, that's where you're gonna do the ortho para addition. However, if your para is open or it's available, it will favor that versus the ortho because of there's less steric hindrance. If it's deactivated, then that's when you do the meta addition. So these are your common activators. Usually they going to have lone pairs. So if you don't know if it's an activator or not, see if it has lone pairs. The only exception if is alkyl groups, so just regular carbon chains. They will be the weakest activator, but they're still considered activators. Everything else has like lone pairs that they can donate. For deactivators, they're going to be meta directors. These are your other, these are your examples. So one exception is the halogen. So deactivators are meta directors. However, halogens, because they have lone pairs, they can stabilize the sigma complex by donating those lone pairs. However, they're still electron withdrawing groups. They're still halogens. They're still electronegative. So they're still deactivators. If you don't know if it's a deactivator or not, look at the central atom. If it's positive or if it doesn't have um, lone pairs, typically it's going to be a deactivator. Like for this nitric group NO2, this is what it looks like. Notice how the central atom is positive. Sulfonic acid, if I resonate it, I'm gonna have a positive charge on the central atom. The same goes with all of these. Their resonance leaves a positive charge on the central atom. Um, if I have a coronary ammonium, I would say this one probably be the strongest because this positive charge cannot resonate, so it's stuck in the um, central atom. Okay, and so here's like the ranking of it. Um, activators versus deactivators. Yeah. Okay. Here's another graph. Halogens, although they're deactivating, they're still orthopara. So these three columns would be orthopara. Right. So if I have multiple substituents, I would put the um, electrophile on the position that can satisfy all substituents or the strongest activator. So for this molecule, I can put it here. It's ortho to a electron donator, and it's meta to a electron withdrawing group. So here in this position, I could satisfy both. However, if I have this molecule, um, this is a NO2 is the deactivator and OCH3 is the activator. The strongest activator being the one that's the activator. That one is the one's doing the activating. So it would be OCH3. So I would try to satisfy this one over this NO2. So that being said, I would look at orthopara. Um, I could attach it here, but there's steric hindrance there. between these two substituents. So I could place it on this ortho position or this pair position. Either one works. All right, so if I want to add an R group, a common way to do it is fieldcraft. The only caveat to that is the ring has to not be deactivated. So you can do it with a regular benzene ring, but if it has any deactivators on it, fieldcrafts cannot happen. You can also do rearrangements like methyl hydride shift. So what happens is, I think, okay. So this the AlCl3 in fieldcraft, it's going to remove this Cl here, and that will give you a carbocation. And so carbocations, think of it like an SN1 reaction. So it's going to do rearrangement to make the carbocation into the most stable position. And so um, once you find a stable position, that's where you will attach that's where you will attach the benzene ring to. Another one is fieldcraft acylation. So it's not acylation, but it's acylation. Acylation just means you're adding a ketone to it, or you're adding a acyl halide to the benzene ring, um, and then you would get a ketone. Same thing, you cannot react with deactivated rings. And so what you can also do, you can have an alkene, protonate it to where you get a carbocation, and you can add it to the ring. You can, yeah, you can use HF for that. You can also use BH4, so kind of the same thing as the one previously. Instead of alkene, it's alcohol. So I can make a reagent a good electrophile by, um, if it has alcohol, I can remove this alcohol group to where I can get a carbocation and I can attach it to the ring. If I want to add an R group, but I don't want a um, a carbonyl, I would do the Friedel-Crafts acylation and then finish it off with Clemmensen reduction, which is zinc mercury with HCl. Right. So with nucleophilic aromatic substitution, the ring has to be deactivated first. So once it's deactivated, if it has a leaving group, so it's usually going to be a halogen, it's going to replace it. So in this case, we do have deactivators and we have a leaving group, so this Cl will be replaced. And then if the ring is deactivated, if you're doing a nucleophilic aromatic substitution, the electron withdrawing groups are going to be orthopara, so it's opposite. It's opposite from electrophilic aromatic substitution. If you don't have a electron withdrawing group, but you still want to replace it, you can treat it with NaNH2, and then whatever nucleophile you want to add. So by doing so, adding NaNH2, I can replace the leaving group, or yeah, I can replace the leaving group with NH2 in this case. Here's the mechanism. I don't think you guys need to know it, but it'll make like a triple bond. Yes, so it's gonna attach to either side of the triple bond. So you're gonna have a mixed reaction or mixed product. If I wanna add a R group, I can also use organocuprates. So I can, if I have a leaving group, if I have a organic group rates, whatever the R group is connected to it, I can just attach it kind of like this. Heck reaction, it's kind of like organic group rates, but instead you are going to attach the double bond to the, you're going to replace the leaving group with the alkene. So your alkene is going to connect to the ring. So kind of like this. And you'd use palladium. Suzuki reaction is this one. Suzuki reaction is, you use the same catalyst, but instead of a double bond or an alkene, you would have like a boron R group. So it's just going to replace this boron group with the leaving group. Yeah, so Suzuki is called Suzuki coupling. So it's just going to combine, it's going to replace the leaving group with the whatever R group the boron has. And other ones are catalytic hydrogenation. Yes, this notes will be posted. This will be recorded. Yes, on YouTube. The links to the files, to the PowerPoints, and the problems that we're gonna do is gonna be linked to the description. But here, once we have H2 reacted with H2 with put a lot of pressure and a metal alkyl catalyst, I can completely remove the double bonds. Another one would be birch. So I would put like a liquid ammonium and alcohol and like a metal, and it's going to make two parallel double bonds. Yeah, so here, if you have electron withdrawing groups, they will repel them. So electron withdrawing groups, so they're going to try to be as far away as this group. If you have donating groups, it would try to be adjacent to it, kind of like this. So almost done. If you want to turn everything into carboxylic acid, I could use side chain oxidation with KMNO4 or chromate ions like Na2Cr2O7. So it will turn any R group into carboxylic acid and aldehydes too. Now, one thing you can't do is T-butyl chains. So if you have a tert butyl, you cannot oxidize it into carboxylic acid. Last one is if I want to make a quinone like this, I would. It'll only work if you have an alcohol. So what chromate will do is it will oxidize this alcohol faster than this alkyl group, so it won't make carboxylic acid here, but it's gonna it'll just turn it into this kind of structure if you have a alcohol. I think that should be it. Do you guys have any other questions before we break out to separate rooms? Do you guys have the problems for the review? Okay, well, it's always good to know it's always a good thing to know for future reactions. But if there's no other questions, Les, can you make the breakout rooms?
Okay, perfect. So I wanted to go ahead and get started with the exam review problems. Let's take a look at the second page. And if you could refrain from moving the pages by yourself because it might erase whatever we end up writing on here. We're going to start with ranking anion stability. What factors do you think would make a difference in anion stability? Aromaticity, that's a good one. So from the molecules that you see here, let's, hold on, let me see if I can get a pen. Let's see if I can do like 1, 2, okay, so 1 starting from the left-hand side. So which of these, or actually let's do A, B, C, D, E. Which ones are aromatic? B is aromatic, okay. And why is B aromatic? Okay. Does anyone have the formula for the number of electrons that we need, or does anyone know what factors make something aromatic and how many electrons we need to consider something aromatic? 4n plus 2, yeah, that's perfect. So if we look at molecule A, how many pi electrons does it have? 6. Okay, so that fits our rule. And then if we look at B, how many pi electrons does it have? 8. And it looks like we're including the anion that's at the top. Does anyone know why we're including the anion at the top? Resonance? Okay, yeah. So that lone pair will resonate with all of the double bonds, and that's how you can consider it a fully conjugated system. So we know our first molecule is aromatic, and our second molecule is anti-aromatic. From all of the three, aromatic, anti-aromatic, and non-aromatic, which ones are most stable to least stable? That's my answer. Okay. Does everyone agree with that answer? Okay, so what would be the most stable anion here? One. I mean, A, yeah, because it's aromatic. Okay, I agree. What's the worst one? Or not the worst one, but the least stable. B, okay. Um, and then for the next, okay, do we have any other ones that are aromatic or anti-aromatic? E? Okay, so what is E and how should we rank it? Aromatic, okay, because it has 6 pi electrons, less than 1. Okay, why less than 1? So electron withdrawing groups on it. Okay, I like that. So if you have a negative charge and you have a group that kind of pulls electrons towards it, do you think that would make that negative anion worse, or do you think it would help stabilize it? So not exactly. If you have an anion and you have, so that means you have a strong negative charge on that carbon. having electron withdrawing groups around it helps pull that negative charge towards those electron withdrawing groups. Like, you know, from OCHEM 1, when you're doing acidity, we said that inductive effects helped with acidity because they stabilize that negative charge among very electronegative atoms like oxygen or fluorine or chlorine or bromine. So it's very similar with this molecule with CF3 here. Does that make sense to everyone? Or does anyone have any questions on that? Okay, so this would be better, so E would be better than A because your electron withdrawing groups help stabilize that charge. Between the two ones that we have in the middle, what are they and how can we determine the stability between the two? Or like what factor can we use to tell which one's better than the other? Degree and allylic. Okay, so for these molecules, are they aromatic, anti-aromatic, or non-aromatic? Non-aromatic. Okay, perfect. And they're both allylic. Um, what we can look at, does anyone know what else we can look at? It's also something we consider with acidity. Yes, yes, conjugation and resonance. So between the two molecules, which one has more conjugation and more resonance? C. Yeah. Does everyone agree with this ranking? C does not have more conjugation. Do you think that I should switch this 3 and the 4? Okay. So let's do 4, 3. Okay, does everyone agree with this? Okay, I hope whoever it was that sent in the list of numbers earlier is able to see this as well. If any of you have any questions, please don't hesitate to ask them at any point during the questions. Why electron withdrawing groups are good. Yeah, of course. So when you have a negative charge, to make it stable, you want to spread it out as much as you can. So resonance is a good way to stabilize a negative charge. So let me see if I can draw it with a different color really quickly. So like for 4, you can kind of spread your negative charge over this whole area because you can switch it with that double bond. With 3, you can spread your negative charge over all these atoms. So that makes it good. With 1, you are doing resonance, so your negative charge is spread over this whole region, but your negative charge is also kind of being pulled by the fluorines. So instead of having all your negative charge concentrated on that one carbon, the fluorines being very electronegative and wanting those electrons helps to spread it out even more. Whereas the 2, it's spread by resonance. Oh, sorry. It's spread by resonance, but it's not being pulled by any electron withdrawing group. So that's why we switch. And then with 3 and 4, 3 has more resonance forms than 4. So 4, you can only resonate with one double bond, but with the one that we marked as 3, you can resonate with 2 double bonds. So you get an extra form. No problem. Okay, so for B, we're ranking by sigma complex stability. Have y'all had practice with figuring out which ones are more stable for activators and deactivators? Okay, perfect. So I will give you, let's see, let's start with 5 minutes to rank this, and then we can come back and talk about it. And while you do that, something that I just want to point out is that you have different kinds of groups attached to these molecules. Um, some of them have an amide and some of them have, well, they both, but some of them are attached directly to the carbonyl and some of them are attached to the nitrogen. So think about whether that makes them an activator or a deactivator and which one is better for your stability. Okay. It looks like we have an answer. So I'm going to go ahead and mark this on our document 15342. Hannah, do you want to explain, or does anyone want to explain why this ranking is right or wrong? So for 1 and 4, yeah. So for 1 and 4, what kind of group do we have attached? Is it an activator or a deactivator? No, sorry, not 1 and 4, 1 and 2. Activator, electron withdrawing group. So for 1 and 2, they are activators. And activators are electron donating groups. Deactivators are electron withdrawing groups. So for 1 and 2, you have activators. For 4 and 5, you have deactivators. So which ones are better for aromatic reactions? Activator, yeah. So for 1 and 2, you have an activator that will speed up the reaction. Which compound specifically? Yeah, so for 1 and 2, it's the nitrogen that's attached to the carbonyl. So let me see if I can color that in a different color. So it's this group that we're looking at. Because the bromine is the same in all of the groups. So those are our activators. And then these are our deactivators or electron withdrawing groups. And then 3 right in the middle has nothing. Between 1 and 2 or 4 and 5, we see a difference in the position of that carbocation. Does anyone know why 1 is better than 2 in this situation? Because it's closer when rearranged its para. And 3 are like, yes, that's perfect. So when you have so I'm going to take 1 for example, and forgive me for my drawing. So we just have a group on this end, and you have a positive charge here. So this positive charge can resonate over to this tertiary position, and when the double bond comes down. But in the second one, that positive charge will always be on a secondary spot. So the fact that you have a tertiary allylic in one is what makes it better than two, which is what will give you your para when you para position when you put in which is what gives you your para position in the molecule. Um, and then the same thing is with 4 and 5, that you get that tertiary allylic position. Does anyone have any questions on B? Where's the orange? So the orange is an electron withdrawing group. And the difference is in what part is attached to the aromatic ring. So in the blue ones, you have your NH, and the NH has a lone pair on it, and that lone pair increases the reactivity of the ring. But in your orange ones, you don't have a lone pair connected to the ring, you have a carbonyl. And that carbonyl has a partial positive charge, which kind of reduces the reactivity of the ring. So you're looking at what is attached closest to the ring, even though both compounds look like amides. Yeah. Okay, so we're going to really quickly go. Yeah, I will come back to that in just a second. I want us to be able to do some reactions really quickly. So for number 2, let's do the first 2 reactions. Do y'all know what this reaction is called? It is Diels-Alder. So let's do 5 minutes again. And I want y'all to fill in the missing reagents for the first 2 only, and then we can talk about it. Okay, wow. I'm gonna give everyone else a moment. If you guys want to go ahead, you can just type 1 in the chat whenever you're done drawing it, or you're done working it out. Don't draw it just yet. I want to give everyone else a chance to work it out. And if anyone's confused or stuck, then that's okay. We'll go through it together. For your test, I don't anticipate mechanisms. I would double check with your professor, because they're the ones that are making the exam, but I don't think that your exam will test you on mechanisms, and not the mechanisms for Diels-Alder especially. Okay, if anyone else has the answer for 2, go ahead and type 1 in the chat so I know when we're ready to discuss it together. I'm not sure what practice tests are uploaded for your professor. So I don't want to say something that's not right. I don't know if they include chapter 18. At the first one. Okay, perfect. So Wahid, do you want to go ahead and draw the answer for the first one? And then Hannah, you can do the second one when we get to it. Okay, I really like this. Why did you put the two nitrile groups in opposite directions? Because wedge and Nash, that's perfect. Yeah, so on the ring, you can't really show cis and trans. I mean, you can't really show um, what conformation the molecule was the way we draw it linearly. So if you see a trans conformation on a cyclohexene by the wedge and the dash, then you know that that half of the Diels-Alder reagent is going to be in a trans alkene position. And if both our nitriles were wedges, then he would have drawn these with both of the groups facing to the left or to the right. That's perfect. Hannah, do you want to go ahead and draw the answer for the second one? Yeah, that's perfect. So one thing that really helped me on tests with Diels-Alder is you're always going, hold on, let me get, okay. So you're gonna have one, let's see if I can make this smaller. Okay, 1, 2, 3, 4, 5, 6. And so you're starting with your original molecule as 1, 2, 3, 4, 5, and 6. So whatever you see on those original molecules, you'll attach onto your final cyclohexene, and if you're working backward, then it's the same thing. So I really like that you added in those 4 fluorines. That's perfect. And then similar question for you, Hannah. For your molecule on the left, why did you draw the group attached to 1 going up and out and the group for 4 going in? Different conformation. Okay. Yeah, that's exactly right. So again, you see on this final molecule that one group is on a wedge and one group is on a dash. So that stereochemistry is important for y'all to show in your when you have your diene in your dienophile. So really good work. Let's do a different type of question. Um, Up is dash. No, not necessarily. Um, You can, yeah, exactly. You could have drawn this with your 1 looking like down and your 4 kind of going out. And that's also correct as long as you show that they're in different conformations. So in your 3D structure, 1 will be a wedge and 1 will be a dash. Um, there's not necessarily one that equals the other. Okay, so let's quickly go over let's go over. Okay, so this question 2 that's on the bottom of the page. Um, so this one has you consider this molecule histamine, and it has 3 nitrogen atoms in it. So I'm going to just ask this, and y'all can reply in the chat. What is the hybridization of N1? sp3. Okay, what about N2? sp2. Okay, and then what about N3? Also sp2. Okay. Um, and in which, okay, let's do the lone pairs. Which orbital is the lone pair for N1 located in? sp3. What about N2? P. Um, okay, Hannah, why is the lone pair for N2 located in sp2? For N2, it can resonate or cannot resonate? Cannot. Okay, perfect. And then what about the lone pair for N3? Cannot P. Okay. So I just want y'all to see that N2 and N3 are both sp2. N2 is sp2 because it literally has like a double bond attached to it. And N3 is sp2 because it can resonate. So even though the molecules are both, or the atoms are both sp2, their lone pairs are in different orbitals. If you can resonate, then your lone pairs are in an unhybridized p orbital. Let's see. Okay, we have one more. Why can't two resonate again? It can't resonate because it's there's already a double bond attached to that nitrogen. So you can't have another double bond attached to it. Which nitrogen is hardest to protonate? We can do it. Which nitrogen do you think is hardest to protonate? Okay, I see that. Why two? 3. Okay, why 2 or why 3? Because it would make it non-aromatic. What we do with resonance. sp3, the third one. So if you deprotonated the third one, it would not make it sp3. It would still be sp2. Both 2 and 3 are 3 is very difficult to deprotonate because your lone pairs are involved in resonance. The second one is also very difficult to deprotonate because it has a double bond on it, and there isn't even a hydrogen there to begin with. Hardest to protonate. Oh my God, my bad. I didn't read the question right. Hardest to protonate. Then yes, it is 3 because of the resonance. Right now you have resonance and it's involved in that aromaticity. Vivian, you're 100% right. When you protonate it, it is now sp3 and it doesn't have that lone pair. So that is the most difficult nitrogen to protonate. Okay, let's see. We have some aromaticity questions and some reaction questions. Would y'all rather do aromaticity or aromatic reactions? Aromaticity? Okay, let's do aromaticity. Aromatic reactions? Okay, we can do both. So let's do number 5 really quickly. I'll give y'all a few minutes. I want you to circle the compounds that will dehydrate readily in acidic conditions. So these are stable compounds. That means aromatic and non-aromatic compounds. And I'll give them letters so that y'all can just write them when you're done. Or you can what's it called? Use the, what is dehydrated? Um, Dehydrate readily means that this alcohol can leave and you would still have a stable molecule left. So for A, what it would look like is that's basically what you're looking at. What's left behind, is it aromatic and non-aromatic? Yes. If what's left is anti-aromatic, then that compound will not dehydrate readily. And whenever you're ready, you can go ahead and comment a 1 in the chat so that we know when we're ready to review. Okay, yeah, we can talk about it together. So let me just pick a different color. Okay, so is A aromatic or non-aromatic? Okay, is A aromatic, non-aromatic, or anti? A is anti. Okay, so anti will not circulate. Is B aromatic, anti-aromatic, or non-aromatic? Arrow. And how do we know that? The carbocation does make it aromatic for B. Each of these double bonds has 2 pi electrons in this, so this has a total of 6, and the first one had 4. But we're looking for sets of 4n plus 2 pi electrons, so that makes B aromatic. If it's just 4n, so like 4 pi electrons, 8, 12, then that would be anti. For C, is this anti-aro or non-aromatic? Arrow, okay. And why would you say arrow? 6 pi, okay, perfect. What about D? Arrow, okay, why arrow? Yes, so for C, even though oxygen has 2 sets of lone pairs, only one will be involved in the resonance, so that's the only one we count. With nitrogen, you only have 1 pair. And then with D, an atom like boron actually has no lone pairs. So in this one, you would have 4 pi electrons, which makes it anti. What about E? Is E anti-aro or non-aromatic? Yeah, that's perfect. 6 pi. Okay, what about F? Okay, 8 pi anti-aromatic. What about G? Arrow, okay. Yeah, that's perfect. So you can kind of see between the nitrogen and the boron, we do count the nitrogen's lone pair, but we don't count, well, boron doesn't have any. So we just count whatever else is there. For H, what do we have? None. Yep. Okay, good job, everyone. So that's what's the hybridization of G. Um, So yes, okay. So the hybridization of boron is sp2. Um, Boron basically, so you have boron, and then you have hydrogen, and then you have three bonds to carbon here. So that gives you just sp2. If you had, so like when you have NaBH4, that's an sp3 boron. But that boron is also negative. So boron is kind of just an odd element. We're used to seeing sp3 elements neutral, but boron is actually neutral when it's sp2. Yeah, so the question is asking which compounds will readily dehydrate in acidic conditions. So to readily dehydrate means that that alcohol will leave and you'll have a carbocation left. Now, an atom is going to do that only when the remaining molecule with the carbocation is a stable one. So we know that aromatic compounds are the most stable and anti-aromatic compounds are the least stable. Anti-aromatic compounds are really, really bad. Like a molecule, it's not just like meh, it's like a molecule is like wildly reactive if it's anti. So if your molecule, so for example, D and F, so A, D, and F actually, those will all become anti-aromatic if they were to dehydrate. So the molecule would not dehydrate because it wouldn't want to G is aromatic and not anti. Um, no, sorry, G is aromatic. Yeah. You're right. I don't know why I wrote anti. It is aromatic. Um, Yeah. So the question, dehydration just means you're losing OH to get the carbocation. And then readily dehydrate is asking you to look for which carbocation molecules will be aromatic or non-aromatic. Um, for F, okay, so we have 4 pi electrons from the double bonds. Do you see that? So we have 2 from here, and then we have 2 from here, and then we get 2 from the oxygen and 2 from the nitrogen. Yes. Um, because like even if we look at B for example, or okay, what's an easier? No, yeah, let's do B. Um, so you will never have the whole molecule be double bonds. So you can keep rotating, but you'll always have a charge somewhere. And this would be for B, and that's okay. So for F, when you have this positive charge, it can react with the lone pairs from oxygen or the lone pairs from nitrogen, but as long as it can eventually do both, you're good. Okay, let's take a look at some reaction questions. So, um, for A, sorry, there's a same form, but it asks deprotonate quantitatively. Okay. Um, Yes, if there's nothing on the molecule, then that would have a negative charge on the carbons. In this case, we had an alcohol, so that alcohol leaving would give you a positive charge. But if you're deprotonating the carbon, then yes, you'd have a negative charge. Yeah, no problem. Um, okay, so let's start with A and B here. For A, what kind of question? So you know there's HBr on a conjugated um, double bond system, and it's at 40 degrees temperature. So what kind of product are we looking for? Yes, that's perfect. 40 degrees means we're looking for the thermodynamic product, which is 1,4 addition. And that means instead of trying to make the most stable double bond, we're trying to make the most stable carbocation, and then add our product. So let me draw this. Um, no, I think that that would also be thermodynamic, just because HV means heat, and when you have heat, that's what you're making. If it was cold, so for example, if this said like negative 80 degrees, then you could do kinetic. But, okay, let's take a look at this. So on this product, what would, you're welcome. Yeah, HV is just heat, or it might just be light. I would double check that. But HV is, hold on. HV is light, but that's usually what it means. So for this molecule, where would you put your positive charge for it to be the biggest? So this is your double bond. Where would you put your positive charge for it to be the most stable? On the 3 substituted. Okay, perfect. So where would you then put your bromine if it's a 1,4 addition? On the top? Do you want to go ahead and draw it? Hold on, I drew the double bond wrong. I think that started that confusion. Hold on. Okay, so here, one second. I'll give you an example of it that's kind of like drawn out. So this is your basic conjugated system. Um, if you are doing 1,2 addition, you would do it right here. Oh, sorry, 1, 2. And then if you were doing 1,4 addition, so where does the 1 start from? Carbocation. Your 1 is starting from, okay, so for here, 1, 2, 3, 4. And here, 1, 2, 3, 4. And you could rearrange, actually here, let me redraw this so that these look equal, my bad. So this molecule at the top starts from having a positive charge on 2, and that's where we put the bromine. And then this molecule that's at 4 starts from having that positive charge on the 4. That 1 just starts from, let's do 1, 2, 3, 4. But for the 1, 2, you deprotonate. I mean, you put the carbocation at 2, and then for 1, 4, you have your carbocation at at 3 and resonate. So let me see if I can draw it. So this is what you start with to make 1, 2. And then when you resonate this molecule, 1 second. That's how you would get your 1, 4. Does that make sense? So 1, 2, 3, 4 is starting from that double bond that you deprotonate. And then the 1, 2 and the 1, 4 molecule, you didn't deprotonate a different spot, and I'm sorry if it came off that way. You just resonate with the carbocation that you created. Okay. Okay, I think we're gonna do B and then wrap it up. B is practice in what we did earlier. Does anyone know what kind of reaction B would be? Diels-Alder. Okay, perfect. And I kind of wrote in the space of Diels-Alder, so if anyone wants to draw below, you can draw what that final product should look like. I'm not sure if we have the time for K right now. I know we have it in the answer key, so if you want to work on that problem after this session, you can double check your work with that. But for now, I don't think we'll have time to go over it in detail. Um, I do think the key will be sent out after this. I am going to quickly see if we can go over K actually, but it is the Suzuki-Miara coupling reaction where you take an aromatic with an equivalent benzene and you get 2 benzenes. This session will be recorded and put on YouTube, so you'll have Frank's presentation and then the breakout session. Um, does anyone want to draw the final product for B? Oh, okay, hold on, let me see. I don't think I was able to see it right over there. Oh, here. Okay, yeah, that's perfect. That is correct. I like the way that you drew the part of the bridge that kind of goes up, and then the two the things that are attached to 5 and 6 basically on one on a wedge and one on a dash. Yeah, they should be on the UTD Pure Tutoring channel. Let me see if I can look it up really quickly. Yeah, we have peer tutoring at UTD, and they have the exam reviews for different subjects recorded and posted there. Yes, thank you so much, Hannah. Um, okay, we will wrap up today's session just because it's getting a little bit late. I apologize that we weren't able to go through more questions. But hopefully y'all are able to work these out and look at the key. And if you have any more questions, you can always drop by peer tutoring on campus. I am not sure what their schedule is off the top of my head, but I do think you can find it on the UTD website. They have like a schedule for when those tutors are available. But I think they probably should be there like during normal 9 to 5 hours in the weekday. So if you're able to come in at around that time, I think that would be good. And then the in-person location is in the basement of the McDermott Library. It's like the biggest room there. So um, if you're not sure about timing, you can always like drop by and just ask them what their schedule is like for the future as well. Um, Hopefully this helped y'all a little bit for your exam. Good luck. And if you have any like specific questions about what will be covered on the exam, I would definitely recommend double checking with your professor as well. Thank you, everyone. Previous practice exams are for Novak. I'm not sure. I think there is a Dropbox that has previous practice exams, but Novak specific exams, I'm not sure. There was an exam review for Dr. Novak, and that is also uploaded on the UTD peer tutoring, on the UTD peer tutoring YouTube.